Hi, today we are going to talk about the importance of standard deviation for calculating accuracy and precision compared to percent error. Before watching this video, I recommend that you learn how to calculate both percent error and standard deviation, and also you look at information related to what is precision and accuracy. To do this discussion today, I've put a set of data here behind me on the board. The data set has a data value of 10, 100, and 190. I've also done some initial calculations, which we'll talk about, which are to the right of the data. The first thing that we want to talk about is the fact that percent error is a bad measure when there is error in a calculation, error already in a data set. So I have here 3 pieces of data, and I have a theoretical value of 100. When I calculate the percent error with this, you would take your numbers and say that the percent error is equal to the theoretical value minus the experimental value divided by the theoretical value. You take an absolute value of that and multiply by 100%. Or add the percent, depending on how you want to handle this. Some teachers will say to you that you will get your decimal percent and then you convert, or some will actually write it out like this. In the end, you want to have your percent out of 100. So to get the theoretical, that is already given. That was given by previous experiments. That was given by your teacher based on a value that came out of the theory related to the topic that you're researching. If you are doing an original science experiment, there is no theoretical value. We'll talk about that a little bit more, but to use percent error, you must have some comparison value that is considered to be the accepted theoretical value. You then want to get your experimental value. Number one, you don't ever do your percent error based off the experimental values individually. You need to average these. So the average value here of our data, so our average value, our experimental average, is equal to 10 plus 100 plus 190 divided by 3. So the experimental average is 100. So with that information, you might already see where this is going, that our percent error is going to be 100 minus 100 over 100 times the 100% to convert it from a decimal percent into a full percentage, and we end up with 0% error. Wow, you did an experiment and you got 0% error. You must have done an excellent job. But then we think about this. If I were giving you an experiment and I said to you, the theoretical value is 100, let's say I want to measure the length of this room, and one student comes back and says it's 100 feet long or 100 meters long. Another student comes back and says it's 10 feet long or 10 meters long. A third student comes back and says it's 190 meters long or 190 feet long, whichever unit of measurement you're using. And you would say, wow, there's no consistency there. Yet your percent error is 0. Percent error does not take into account the fact that data itself could have error. What it does is it takes the average of the data and says that your average measurement was 100, so your percent error is going to be 0 in this case. A broken clock is right twice a day. This is a prime example of dumb luck. If I did this experiment again, I don't think I could predict what the next person's measurement. If there's a fourth person taking a measurement, I would have no clue what their measurement would be. Would it be 100? Would it be 200? Would it be negative 50? What would that next measurement be? A precise piece of data has all the data points very close together so that you can predict that future measurements are going to fall within in the same range. I have no idea where this data is going. The next piece of this is to talk about the standard deviation. So what I've done here is I've taken the deviations and then I have squared them to get my deviations squared. We will add them up and we will get the variance. The variance value for this is going to be 190. It is going to be 162,000. I'm sorry, 162,000. Therefore, when I do the standard deviation, I would have a value of 162,000 minus 3 data trials minus 1. So I end up here with a standard deviation of 90. And then my standard error would be 90 divided by the square root of 3, which ends up equaling 51.96. This value of 51.96 represents the accuracy measurement, and the standard deviation is going to represent the precision measurement. We write these, whenever we want to write the standard deviation or the standard error, what we want to do is we want to write it based on the average value. So this would say the right way to write this would be to write it as 100 plus or minus 90. That is your standard deviation. And the standard error would be 100 plus or minus 51.96. You could see there that the standard deviation value is extremely large compared to the average measurement. That average measurement value, if it was 1,000,000, 90 is not a big deal. But if it is 100 and your error is 90, then that is a big deal. And so what we're going to say is that there is going to be an acceptable percent of this value that is acceptable percent of this value here that would define whether or not the data is precise. In my class, it is going to be 5%. So if this value is less than 5% of 100, so 5% of 100 is 5. So if this value is less than 5, then I would consider the data to be precise. This is much larger than 5, so I'm going to consider this data to be not precise. One of the things that you should note is that this method that I'm using of just saying 5% is a little arbitrary. The correct way to do this would be to use a t-test. We are not going to go down that road in this particular course, but this idea of just saying that the standard deviation should be, to be precise, should be less than 5% of the average value is a good approximation, and that's what we're going to do. We're going to use the standard deviation to figure out precision and get a good approximation of whether or not our data is precise or not. The standard error is 51.96, and what that says is that if you take 100, that you would have a value of 100 minus 51.96, and you would have a range up to 100 plus 51.96. That gives you a range to see if your theoretical value falls within there. The theoretical value does fall within this range of 100 minus 51.96 and 100 plus 51.96. And that's what this means, 100 plus, 100 minus. If the theoretical value falls within there, we could say the data is accurate. Sometimes our data is accurate and not precise. Sometimes our data is precise and not accurate. Sometimes it's both precise and accurate. Sometimes it's neither precise nor accurate. Either way, you need to be able to evaluate. What we would say with our data here is that our data is accurate. 100 does fall in there, and your data would be around the bullseye, but it is not precise in this particular problem. It is important that we have precision. Ultimately, in science, having both accuracy and precision is what we want, but if we have to sacrifice accuracy or precision, you sacrifice the accuracy. Having precise data is extremely important because that tells you that there is a pattern. Having accurate data does not give us any way to predict future measurements. If our data is precise and we have multiple measurements that are precise, we can then predict that our next measurement should, within the appropriate statistical value, fall within the acceptable range. And so if this was 100 plus or minus 4, then we would say that our next measurement would have a high probability to fall within 96 to 104 in measurement. Because our data has so much error in it, it doesn't give us anything valuable to make future predictions or to figure out where the data came from and go back in time and figure out what might have happened before the experiment. Depending on what type of experiment you have, you could be trying to predict what's going to happen in the future, or you could be trying to figure out what happened in the past. So a percent error of 0 right here gives us no good information to make predictions for the future. And therefore, percent error is not a good measurement. We would try to avoid this whenever possible, and we will move towards doing standard deviation and standard error for precision and accuracy.